Hello everyone. Welcome to the GPU Teaching Kit. This kit is the result of a collaborative effort between NVIDIA and the University of Illinois to enable hundreds of universities to teach their students of GPU programming. We're going to start with the course introduction today. The primary goal of this course is to teach students how to program heterogeneous parallel computing systems. The obvious goal for this kind of programming is to achieve high performance, but it's also very important in today's energy limited environment to be able to achieve high energy efficiency. We would like to help the students to achieve these goals while maintaining their functional correctness and the maintainability of their software. We would like to also teach students the principles behind the scalability and portability so that their software can be scalable across future generations and also be portable across vendor devices. Specifically, there are three kinds of subjects we're going to cover in this course. The first one is the parallel programming API, tools, and techniques. And these are the mechanics for the students to be able to get into the programming work. And the second one is the principles and patterns of parallel algorithms. This is really the meat of the course. The students will be able to use these principles to be able to engage their real applications and apply these principles to their individual problems. And the third one is for the students to understand processor architecture features and constraints so that they can more successfully reason about the performance effect of the decisions they make in their programming process. Many people have contributed to this teaching kit, and in fact, this teaching kit has been in the making for the past several years. My name is Wenmei Hu, and I'm going to be the principal instructor and training resources for all the instructors who will be teaching this course to their students. I would like to acknowledge my co-author, David Kirk. He has been co-authoring textbooks and the teaching material for the past several years. The next two people I'd like to acknowledge are Joe Bungle and Mark Ebersol, who have spent an incredible amount of effort specifically to help us to build towards the release of this teaching kit. And the next two individuals are Abdul Dakak and Izzat Al-Hajj, and they are my PhD students who have been the primary people who put together the lab and the assignments and the infrastructure. Andy Xu is the person who have been managing the entire teaching kit process. And the next several individuals, John Stratton, Izzat Gelado, John Stone, Javier Cabezas, and Michael Garland. And these are the people who have all contributed whole or part of lectures that I'm going to be covering in this teaching kit. The GPU teaching kit is going to have a fairly extensive coverage of topics. The whole course is going to consist of almost 30 modules, and each course could consist of the entirety of these modules or subset of these modules. So I'm going to give a very high-level overview of these modules so that the instructors can begin to consider which modules to include in their own courses. The first module is a course introduction where we introduce the general concepts of heterogeneous parallel computing and the important considerations when developing software for heterogeneous parallel computing systems. In Module 2, we start to introduce CUDA-C. We start with the general landscape and where we compare between language approach, library approach, and compiler directive approach. And then we zoom into CUDA-C we discuss the basic APIs, and we start to introduce the concepts of data parallelism and threads. And then we give a little bit of overview of the CUDA toolkit so that with the students can begin to develop code. In Module 3, we start to introduce the CUDA parallelism model, where we first start with very simple kernels, and then we go into more sophisticated kernel configurations, and then we give some simple examples and more sophisticated examples. We also will introduce the thread scheduling mechanisms behind the parallelism model. In Module 4, we introduce the memory model and locality. This is where we're going to begin to look at how we can use limited fast memory resources to conserve global memory bandwidth. And this is how we can achieve very high level of parallelism and performance in the presence of limited memory bandwidth. But we also need to look at some subtleties in terms of boundary condition handling and so on when we try to exploit locality. Module 5 is performance consideration when it comes to kernel-based parallel programming. And we're going to look at control flow and scheduling implications. Module 6 is concerned with the performance considerations with respect to global memory. We'll start with limited global memory bandwidth, and then we would explain how we can maximize the utilization of limited global memory bandwidth when we access data in and out of DRAM. Module 7 introduces atomic operations, a very important form of synchronization in parallel execution. Module 8 is the introduction to the convolution parallel computation pattern, and in a form of pattern that is what we call the stencil computation. And Module 9 is where we analyze tiled convolution algorithms, and especially focusing on the analysis of data reuse efficiency in these tiled algorithms. Module 10 is concerned about the performance considerations in reduction trees. And this is a very important parallel computation pattern where several important performance considerations need to be incorporated. Module 11 is about a scan computation pattern, and we will introduce the concept of work efficiency in parallel computation. Module 12 is a in-depth analysis of some performance considerations between algorithms that we can select in order to implement the same computation. For example, we can use a parallel scan versus using or use atomic operation to accomplish the same histogramming computation. And Module 13 covers some advanced memory model considerations, especially the special memory memories such as constant memory and texture memory. Module 14 touches the fundamental considerations of floating point computation in parallel computing. We especially focus on the numerical stability of parallel algorithms. And Module 15 introduces GPU as part of a PC architecture, and so that we teach students enough about the interconnect of within a PC system, so that students can better understand the reason behind some of the data copying, the overhead, and some of the more recent development of the CUDA-C support to eliminate some of these overhead. Module 16 is on the efficient host device data transfer. And this is where we start to go beyond just the data parallelism and discuss the task parallelism support in CUDA using streams so that we can effectively overlap the data transfer with computation. And we also discuss some of the subtleties, such as using pinned host memory to improve the data transfer bandwidth. Module 17 covers an application case study of MRI reconstruction, and Module 18 is yet another application case study on electrostatic potential calculation. In both of these case studies, we show students two concrete examples of how one can engage a real application and apply many of the principles that we learned in this class to be able to achieve a good performance result in these real applications. We also compare and contrast some improvement steps by converting from one the type of algorithm to the next type of algorithm, the benefit that we can expect from each. Module 19 is an introduction to computational thinking. And this is to go beyond algorithms. This is for students to begin to think about how they can think about the formulation of their applications into computation problems in such a way that they're more amenable for parallel computation. Finally, we would get into several related programming models. The first one is MPI, and we focus on how a student can develop a joint MPI CUDA program that so that they can take advantage of the increasing number of clusters with GPUs as in each node. Module 21 introduces CUDA Python and show the students how they can benefit from GPU acceleration when they write Python code. And Module 22 is a related, introduces a very closely related cousin of CUDA C, which is OpenCL. And Module 23 shows a OpenACC as a closely related programming model. Especially once students understand CUDA C, they can actually reason about the compiler directives of OpenACC and envision the parallel execution or the compiler implementation of these parallel execution derivatives much more effectively. Module 24 covers related programming models, which is OpenGL, and this the contents of this chapter focus on how one can use both OpenGL and CUDA in the same program, so that the developer can use CUDA for the computation aspect and OpenGL for user interactions and graphical aspect of the application, so that we can build very engaging and interactive application. Module 25 covers a new trend, which is the dynamic parallelism support in new generations of GPU architectures. And this allows the kernel to be able to create additional parallelism or additional kernel launch without the host support. And this decreases the overhead and latency of implementing, for example, hierarchical computation methods. And Module 28 that introduces the basic techniques and some of the tools for using multi-GPUs in the same system. And this is becoming increasingly important as applications such as deep machine learning and deep neural nets that require low latency collaboration between GPUs to be able to increase the speed and the efficacy of the training. Module 27 introduces several important CUDA libraries. For example, CUDA linear algebra library cuBLAS, and CUDA FFT library CUFFT, and then some solver libraries, which is CUDA solver. Module 28 introduces more advanced material about using thrust as a parallelism algorithm library. And module 29 introduces a complementary GPU development platform, which is QuickLab. This complements the primary development platform that we're using in this teaching kit, which is what we call the web GPU. So this gives a very quick but hopefully informative overview of all the modules that we're going to be including in the teaching kit. And I look forward to working with all of you to deliver this course to your students. Thank you. GPU programming. This is the end of the introduction to the toolkit. Thank you.